Imagine an animal that freezes solid. Not just a little bit cold, but with ice crystals forming in its blood, under its skin, and in its abdominal cavity. For the North American wood frog, Rana sylvatica, this isn't a hypothetical, it is an annual survival strategy. As winter approaches, the frog doesn't burrow deep enough to escape the frost. Instead, it finds a shallow spot in the leaf litter, lets the cold seep in, and prepares to turn into a solid, frozen block. The fundamental problem with freezing, for any living thing, is that water expands when it turns to ice. Ice crystals are sharp, jagged structures that would normally shred a cell membrane from the inside out, causing catastrophic damage. Yet, the wood frog survives. The secret isn't in preventing the freeze, but in controlling it with an ingenious biological antifreeze. The moment the first ice crystals touch the frog's skin, a signal cascades through its body. Its liver begins a process of almost unbelievable metabolic conversion. Glycogen, the stored form of glucose in animals, is rapidly broken down and flooded into the bloodstream. Within hours, the frog's blood glucose levels can skyrocket to levels 100 times higher than normal, reaching concentrations that would be lethally toxic to a human. This isn't just sugar, it's a cryoprotectant. The glucose permeates every cell in the frog's body, from muscle tissue to the neurons in its brain. This syrupy sweet cellular environment is the key to managing the ice. This high concentration of glucose inside the cells dramatically lowers their freezing point. More importantly, it creates an osmotic imbalance. Water is drawn out of the cells and into the extracellular spaces, a process called cellular dehydration. This is a crucial trade-off. The cells shrivel and shrink, but the water that could have formed deadly ice crystals inside them is now safely outside. As the temperature continues to drop, this extracellular water is what freezes. The frog becomes a composite material, a network of shrunken, syrupy, unfrozen cells suspended within a solid matrix of external ice. Up to 70% of the water in its body can become solid ice, yet its vital cellular machinery remains pliable and intact. As the ice matrix forms, everything stops. The frog's lungs cease to function. There is no breath. The heart, which had been pumping sugary blood, slows, sputters, and eventually goes completely still. For days, weeks, or even months, there is no heartbeat, no blood circulation, and no discernible brain activity. If you were to find one in this state, it would be cold, hard to the touch, and by every clinical definition used for humans, it would be considered dead. It is a state of profound suspended animation, a metabolic arrest where the chemistry of life is put on hold, preserved by the cold and protected by sugar. Spring's arrival triggers a reversal that is just as remarkable as the freezing. As ambient temperatures rise above freezing, the ice begins to melt. The process starts from the inside out. The heart thaws first. Within about an hour of internal thawing, it begins to beat again, feebly at first, then with more strength. It starts pumping the glucose-rich blood, which still saturates the frog's system. This blood serves two purposes. It circulates warmth to the rest of the body and delivers a massive, ready-to-use energy source to waking cells. Breathing resumes, muscles twitch, and within a day, the frog can be hopping around as if nothing happened. This process isn't without its risks. The state of being frozen and the subsequent thawing creates significant physiological stress, particularly from ischemia, a lack of blood flow, and reperfusion injury when blood flow returns. To cope, wood frogs have elevated levels of antioxidant systems and specialized proteins that are ready to repair cellular damage caused by oxidative stress the moment things turn back on. They also have mechanisms to manage blood clotting, which could be a major problem when circulation restarts after a long pause. It's not just a freeze and thaw trick. It's a whole suite of interconnected biological systems designed to manage and repair the consequences. This natural solution points directly to a major challenge in modern medicine: organ preservation. A human heart or lung intended for transplant can only survive outside the body for about 4 to 6 hours. A kidney might last a day. This incredibly short window is a race against time, limiting the distance an organ can travel and leaving no room for delays. The reason for this limitation is the same reason a frog should die when it freezes: cellular damage. Once deprived of oxygen and nutrients, cells begin to break down. Cooling slows this process, but it doesn't stop it. Simply freezing the organ would cause ice crystals to destroy it. So, how can we replicate the frog's success? The goal in cryopreservation is not just to freeze, but to achieve something called vitrification. This is a process where a liquid is cooled so rapidly that the molecules don't have time to arrange themselves into a crystalline lattice. Instead, they become locked in a disordered, glassy state. Vitrified water is an amorphous solid. It's hard like ice, but lacks the sharp, destructive crystals. To achieve this with something as large as a human organ, scientists combine rapid cooling with high concentrations of cryoprotectant chemicals, synthetic compounds that perform the same role as the frog's glucose. They prevent ice crystals and protect cells, offering the possibility of banking organs for days, weeks, or even longer. The wood frog provides the biological proof of concept for a technology that could one day redefine the boundaries of life, death, and transplantation.
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.